Okay, so in the previous video we talked about why electric charges move through electric potential energy, and then that causes motion of electric charges. Now I just want to go back and review, and we're going to start talking about, well, what does this movement mean, and what is it? How do we get electricity from it? So before, this is the circuit that we had. We had the battery here, which is our voltage source, and the electrolyte inside the battery splits the positive and negative charges, and it places the positive charges on the cathode of the battery and the negative charges on the anode of the battery. And then this split in charges actually creates an electric field. And the only way that we can get this to go back to normal is if one of the charges moves through our circuit and then back to the other side. And so this is why we have electrical current. This is why we have electricity. And so I want to go ahead and start by defining, well, what is electricity? Okay, so electricity is just the movement of charges. So anytime we have a charge that is able to move, we have an electricity. We have electricity. Now we define this movement as electrical current. And we're gonna define that as being the amount of positive charges that pass a single point in a circuit in 1 second. Okay, so if I were to look at a wire in my circuit, so I'm going to zoom in on this little spot right here that's going to come out here. The wire is going to look like a cylinder. And then if I were to pick one little spot in here, and I were to count all of the charges that come through, so I'm going to count right here in 1 second. So the number of charges that come through in 1 second, that would be my electrical current. Okay, so it's the amount of positive charges that pass a single point in a circuit in 1 second. And so that doesn't look like it is 1 second. Okay, so we actually have an equation for electrical current, and so we have current, which is what you'll hear me refer to it as, is just current, and that is given the variable I equals the amount of charge, Q, divided by time. And so this will be our first equation of the video. So current equals charge divided by time, or the amount of charge that passes a single point in 1 second. Now the units are amperes. You've often heard them told as amps, or they get the units of capital A. Now 1 amp is a lot. That's 1 coulomb of charge every second. And we've learned before that a coulomb of charge is enormous. So 1 amp is a lot. As a matter of fact, it only takes 2/100ths of an amp to kill you. So this is the lethal amount. Lethal, L-E-T, let's erase that, L-E-T-H-A-L, lethal. There we go, the lethal amount. So 1 amp is a lot, so you very rarely will see 1 amp. Now there's 2 types of current. 2 types. And these are based on, well, our own errors in our assumptions at the beginning of electricity, or our discoveries into electricity. We have the conventional current, which states that positive charges move from high potential electric energy, electric potential energy, from high electric to low electric potential energy. So let's erase that, L-O, low electric potential energy. Sorry, got a little tongue-tied there. So conventional current says we have positive charges that move from high electrical potential energy to low electrical potential energy. And I'm going to trace that out in blue on my circuit here. So that means that the blue line here traces out conventional current. Okay, and it goes from the positive side of the battery, which has a higher electric potential energy, and then down to the negative side of the battery, which has a lower electric potential energy. Now, the next type is called electron flow. Now, electron flow is actually the newer concept in the fact that if we were to look at an atom, and so I'm just going to draw a basic atom with a positive charge in the middle, and then a negative charge here on the outside, or the electron. So there's the electron, there's the proton's positive, and the electron's negative. Okay, now this is just a hydrogen atom, and you very rarely see a hydrogen atom in this kind of scenario, but essentially it's the same thing. If I were to remove a proton from an atom, well, it's very hard to do. So to remove a proton, as a matter of fact, you cannot. Well, if you remove a proton, you get the atomic bomb. So you cannot remove a proton. All right, so you cannot remove a positive charge from an atom, but the electrons, on the other hand, are on the outside, and so these are easily removed. Okay, and in wires and stuff like that, or metals, these electrons are actually they're actually allowed to move throughout the piece of metal. And so if I were to draw a piece of metal here, and so like this represents one atom, and that represents another atom, and another atom, and another atom, so on and so forth. The electrons from these atoms, or the valence electrons, are actually allowed to move themselves from one atom to the next. And so we actually have this sea of electrons. And that's actually what we call it. We call this sea of electrons. And so these atoms are allowed to move from atom to atom, and they just move throughout this whole thing. So whenever we have metals in a solid form, their electrons are allowed to move. Overall, the net charge is neutral, but each individual atom might have a positive charge or a negative charge at any given time. And so electron flow is just that, the flow of electrons from low electric potential to high electric potential. Okay? And so I'm going to draw that in red. And so that means the electrons come out of the negative side of the battery and flow through our load and then back to the positive side of the battery. And so this is electron flow. This is conventional current. Okay. So those are our two types of current. Now there are many different types of material that can I don't like that. All right, so let's talk about electrical materials. Okay, so if we were to try to pass electricity through various objects, we'd find that some of them are very good at passing electricity, some of them are very bad. And so this is actually a long spectrum, or a broad spectrum, of what we call conductivity. So we'll call this conductivity. Okay, so there you go. Now, at the low end, so the down here, these do not conduct electricity. So do not conduct, all right, electricity. These are called insulators. Okay, at the high end, these conduct electricity perfectly. Okay, and we'll call these we'll call these superconductors. So these are called superconductors. Okay, so we have insulators down at the low end, and these do not conduct electricity. We have superconductors at the high end, and these conduct electricity perfectly. So, in the middle here, we have semiconductors. So towards the insulator side, we have semiconductors. And these right here, I'm going to pull this arrow down here. These conduct electricity only when given enough electric potential. Okay, so think of it this way. If I were to have a gravitational potential, and that's a terrible line. All right, let's say I have a gravitational potential, and I have a block up here. Now this block has gravitational potential energy, but it's not going to move due to friction. So let's say it's not going to move due to friction. Now as I tip this up and I give it more and more gravitational, if I were to give it more and more gravitational potential energy, eventually it would move. And that's kind of the same thing here. The electrons are not going to move because they're being blocked enough, but if I push them hard enough, eventually they're going to say, okay, we're going to move now. All right, here we have the range of normal what we call conductors. Okay, now conductors allow electricity to move easily, but not perfect. So these are easy, but not perfect. Okay, now the majority of copper, gold, aluminum, these fall under conductors. Insulators would be plastic or paper or wood. Semiconductors we know is silicon and germanium. And then superconductors are very special cases of mercury and other various materials that we are continuously working on trying to find, because that's a very important thing that if we could get that, that would be it would save a lot of energy. It would save a lot of energy from being wasted. Okay. Now let's talk about, well, what do these mean? What does it mean on this scale? And so on the superconductor side, there is no what's called resistance. Okay, and on the insulator side, this is large resistance. Okay, so we have no resistance on the superconductor side and a very large resistance on the insulator side. Now let's talk about what is resistance. All right. Now resistance is the slowing down of electrical current in a circuit. Okay, so if we have a resistance, we have a slowing down of electrical current. Now the reason why is because if I were to look inside a wire again, okay, and so here's an atom of the wire, and there's another one, and let's see, right there, and right there, and right there, right there, right there. We have all these different atoms in here. And so I'm just going to fill this wire up with atoms. And then I'm going to put an electron in here, so let's go with a blue electron. So here's my electron. And now this electron is actually going to move through the wire. Now what's going to happen is this electron can't go in a straight line. It's not going to go in a straight line. But even if it does, it's going to hit an electron, or this atom right here. So it might hit this atom right here and get stuck and for a little bit and then bounce off. And so it's going to get stuck, and let's say it bounces off in that direction and it hits that one. And then it bounces off and hits this one, and then it bounces off again and hits back here. Well, if you notice, every time we hit something, we lose a little bit of energy, which means we lose a little bit of voltage or electric potential energy. And so it gets slower. Now, resistance depends on quite a few things, and actually we're going to do a lab over that that you're going to have to complete and look at other ways that can affect resistance. But anyways, as we can see, because the electrons do not have a perfect path, they tend to run into various atoms and get stuck or slow down, and that's the cause of resistance. Now, sometimes these are so great where they don't even allow the electrons to pass through them, and then you get an insulator. And then sometimes we actually can get to a point where we actually line all our atoms up neatly. So let's draw another wire here. We can actually align all of our atoms up neatly. Right? And because they're neat, we can actually push an electron right through. So let's grab another color for the electron. In this case, I have a red for electron, but there we go. So this would be a superconductor.